Hi, he's Gromit and I'm Wallace. And this is the Unstable Fluid podcast.
Yeah, I was going to say, you forget a bit there.
Yeah, it's been so long I forgot the name.
Well done, well done. How are you doing?
I'm doing good, Thomas, thank you. How are things?
Yeah, not too bad, not too bad. Been far too long since we've done this, though it's probably actually technically longer for us than it has been for viewers, because there was definitely a really prompt release of the last episode after we recorded it. Definitely wasn't like 4 months.
Yeah, although that does imply that you're going to put this one out promptly. You could outdo yourself and we could release the next one even later.
Happy Christmas, everyone.
I can't believe it's 2026 already.
You know, I'm finishing my PhD next week. For the record, I'm not. I'm still miles away.
So at time of recording, how far through your PhD are you? How is it going?
Oh, jeez, how far am I, actually? 1 year, 8 months, I think. Yeah,
Excellent.
That's how time works. It might be 9 months. I'm not sure.
So definitely in your second year, well into your second year.
Well
of
into
PhD.
second year, yes. It's going pretty well. My first paper is so nearly ready to submit. So nearly ready. I do now have actually all of the comments back from my co-authors. So it is now just a matter of, it is my job to address these comments and then actually submit the paper. So, like, it should happen, touch wood, in, like, the next month or so.
Okay, so by the time that this podcast episode goes out, you might have submitted a paper.
Maybe by the next one.
Just to be safe.
Yeah, just to be safe. I don't know, actually, if this one rocks up about Christmas, then I probably will have.
We can hope. If you haven't, it happens. I mean, in terms of finishing PhD papers, I just finished submitting a PhD paper, and I finished my PhD last year.
I mean, actually, to be fair, that's like, yeah, I mean, I know people that finished around the same time that haven't got papers out yet either. It's like, it takes time.
It's a surprisingly common event, I think. You shift focus on either, writing papers in the early stages, and then once you start getting towards, thesis write-up, that takes precedent over doing anything paper related. Yeah, I have reviews back. So it's I think this one got submitted actually just before Christmas. Maybe I don't even remember. The process itself takes so long that maybe you'll get it published by the time that you finish.
Actually, yeah, that's a good point. It's like, as much as I say, like, I'm going to have the paper out, it's a paper that's going to be submitted to a journal and then put on Archive, the preprint server. Like, it's not like it's going to have gone through peer review by the time we've got the next episode out.
It might.
I mean, it might, but I don't, I'm not convinced. Because, like, if I'm submitting it in, like, May, that's going to be getting to the point where people start going on holiday and it gets harder to find a reviewer.
This is very true. The classic flaw of academia, requiring peer review.
I mean, it's a generally good thing, right?
It is generally a good thing. It is a massive flaw in the system as to how we expect everyone to do it. So a bit of behind the scenes for academic papers. Generally speaking, the editor of a journal might get paid. It might be part of their job criteria, but it'll be sent out to reviewers, and the reviewers are typically other academics in the same or similar field. And it's normally done as an extra addition to your role. So typically you don't necessarily get hours for it. It sort of comes under the collegiality, contributing to the general academic environment. So expecting reviewers to turn around quickly is very difficult. Normally it's about 6 weeks, I think I've seen as long as, or as short as.
Yeah, the fastest I've ever heard was somebody got one back in, I think, about 3.5 weeks, and that was exceptional. But I know other people that have, like, waited longer than that for them to find a reviewer who would accept it.
Assuming it goes to the editors and then goes straight to a reviewer, and the reviewer accepts and goes straight forward. It can be... There are specific journals that are intentionally fast, and they'll normally limit turnaround, like paper length. So one of my papers is in Journal of Fluid Mechanics Rapids edition, which just sounds cooler and is pun on fluid dynamics, so of course it is. And I think that one was like 8 weeks total, around about, they said. So we had complications with ours, because of course we did, so I think it was more like a few months. But in theory...
Yeah, I mean, we have, like, letters papers, which are, like, normally about maximum about 5 pages. And yeah, those tend to go through a bit faster. But no, mine is going full-on monthly notices, Royal Astronomical Society, which it's like a 12-page paper. It's going to go through the full normal glacial pace review process.
Out of curiosity, because those numbers are quite small, what's the typical paper length in your field?
I mean, they range massively. This one's not ridiculously long. It probably sits somewhere closer to the median, but not the meanest, because we get some papers that are stupidly long. But yeah, in terms of the sort of thing where it's like, this is mostly analyzing existing simulations, this is probably fairly average in length. If it was a more substantial thing of I had done a lot more in either running the simulations myself and setting all those up, or it was a more unusual method I'd had to devise as opposed to it being primarily data analysis, then those papers tend to push up towards the sort of 20 to 22-ish. But we have this whole thing in astronomy of up until fairly recently, when journals went a bit more open access at the point of reading, but it means that the authors then have to pay to get published. Up until very recently, like monthly notices had a 20-page limit, and then you had to pay for additional pages. So it kind of limited a lot of astronomy papers to less than 20 pages.
Oh, interesting. That's valid. I think that's a reasonable concern. I find it interesting because I ask, so I would say a lot of the papers I read are easily the 20 to 30 page mark. I think a few 30 plus, but then that starts getting a bit ridiculous, but less than, say, 18, and it would be considered quite a short paper. But it's interesting as I'm moving around with my role, doing different fields, seeing different, like cultures, like research cultures, I think is what I'm trying to say. So different fields do very, very different things stylistically with their papers as well as with their research, like practices, which is cool.
I presume a maths paper presumably has quite a lot of equations in it.
Yes, funnily enough.
So a typical equation probably takes up a decent amount of space on the page.
That's true.
The page count on mine is boosted by images because I work in galaxy simulations. We make a lot of pretty pictures. But I suppose it's sort of think of like where I would have a massive wall of text, you might have like a few lines of equations.
Yeah.
So that may contribute to, I guess, the longer paper length. But yeah, I don't know, it's interesting.
Although by that logic, that means that probabilists, or in my experience, that means that probabilists have the most maths because their papers can be up to like 90 pages.
Oh, they just like the sound of their own voice in paper format.
I make no comment. Any friends I have that are probabilists, that was Thomas, not me.
What have you been working on?
So I think previous episode was I just started in my new role, settling in, starting some research. I have just finished said research project, so I have been doing a collaboration over the last 6 months with some people over in biomedicine, doing some simple statistical data visualization-y stuff, which I am leaving intentionally ambiguous for reasons. And yeah, that was really fun. It was such a completely different experience to my PhD.
Because it was actually stats.
It was actually stats. It was collaborating really interdisciplinarily.
I can't say that word either, don't worry.
Interdisciplinarily.
Yeah, that sounds...
I think that's too many words.
Yeah, close enough.
Yes, like seeing, I think a lot of maths is, especially applied maths, is like, let's take a real world system and reduce it down and simplify it. And like, especially in fluid dynamics, it's like, okay, we know the Navier-Stokes are there, but when we do the mathematical fluid dynamics, we like throw away a load of stuff that is irrelevant to the specific thing that we're looking at. So whether we're looking at a high pressure system, we yeet everything else.
Context for people who don't work in fluid mechanics, the Navier-Stokes?
Navier-Stokes equations are a series of governing equations that dictate how fluids moves, and it is well believed or well accepted within the field. It's currently $1 million if you can prove it, that the existence of the solutions persist for all time?
Something like that?
I forget what the actual thing is. I wrote it in my thesis. I cited the Clay Institute in the thesis just to be like, the Navier-Stokes, see here. But they are like the governing equations that you can throw everything into, and you output a fluid given initial condition. A lot of us, as a really big equation, throw out a load of stuff and then look at an idealized system. And a lot of my research up till this point has been looking at ideal systems. So like making things simpler, reducing the size of them, reducing the number of terms, like let's make it as nice as possible to play with. And then you get to talk to experimentalists and people in other fields and people working sort of either in industry or government or whatever. And you can't just take the ideal solution. They're like, that's nice, that's interesting maths, but like they need a solution to their problem.
Funny that.
So you actually have to make it real world. I know, right? How dare they not just pay me to have fun? But yeah, so having to kind of balance the good, reliable maths is idealized, and the real world needs fixing, which is a comment more broader than just my research, but anyway. And then, yeah, trying to find that balance has been challenging, but exactly the sort of research that I wanted to be working in. Like, I like that it's a really hard puzzle to solve.
Sounds awesome. So you said you've sort of finished that project. What's next? So
the way the job typically works, so all of us working as innovation research associates, as we are called, we are all on different projects for different percentages of our time, so sort of working on a few different things. I currently am on a project looking at soft matter and hydrogels and microfluidics, so I'm back in fluid dynamics, which is awesome, but a completely different bit of fluid dynamics to my PhD. So looking at the PhD, multi-layer fluids, really cared about waves, really cared about viscosity and pressure-driven flow and all these different terms. And now I'm looking at really, really small things. And when things get really, really small, they kind of stop behaving normally. So I'm in a regime called Stokes flow, which take another random old dude and name an area of maths over him. Also, the Navier-Stokes. No, that's weird. The Navier-Stokes. I'm now looking at Stokes flow, which is very... the way it was described to me, I'm still trying to wrap my head around it a little bit, was like instead of Newton's second law, it's modelled after Newton's third.
Which is the every action has an equal and opposite reaction, rather than mass times acceleration. Okay, I'm having trouble visualizing that, but sure.
Essentially, it's like things don't really have, there's no like inertia in the system.
Inertia being its tendency to keep going.
So things are really like reactive to their environment. So given, say, a really thin filament, and I say because that's exactly what I'm looking at, take a really, really thin like filament, so like a piece of string, and put it in some honey. Bear with me. The shape that the filament takes is basically dictated by what the honey is doing, but everything's moving very slowly. So it's all reaction forces happening rather than, say, if the filament was in a wind tunnel, or like if I was blowing a hairdryer at it, that's when the air is causing the thing to move in reaction to the air around it. In the honey, it's a lot more sedentary and sticky. And I'm going to get shouted at by my colleagues for this very bad explanation, but my justification is I've just started looking at it. So if anyone has a better demonstration, the thing in my head I picture is string in honey, not string in a hairdryer now. New area of research, but also vaguely familiar, so it's nice to get back into that.
Yeah, it's always nice to go back to something that you sort of have spent a lot of time on, but it's been a while. You're obviously back in the world of fluids. Shall we maybe talk about some?
That sounds good. That sounds like a lot of fun. Thomas?
Yeah?
Why is space flat?
Okay, you're gonna have to tell me what you mean by flat, because that can mean different things to different people, and I do not want to get into cosmology today.
Cosmology being...
expansion of the universe, that sort of side of things. Because I don't fully understand
Is the universe flat?
Yes, but I can't remember why.
Okay. I was thinking more in terms of, so, like, accretion disks.
Yes.
Like, when you draw it, there's like a ball and then it has a thing. Or like, Saturn's rings and stuff. Why, when things are being thrown around, do they go flat?
Okay.
And
okay.
Tell me more.
So, to paint a picture for people listening, when we say an accretion disk, this is essentially a big spinning platter of stuff, mostly gas and dust. You get them around stars, you get them around black holes. If anyone's seen the film Interstellar, there's the big black hole in Interstellar that's got the really bright accretion disk that's hitting in a disk around it, and then you've got the bands around the black hole. I will get onto that later. we get a lot of these flat systems in the universe. Other examples include solar systems. All the planets in a solar system orbit in, roughly speaking, the one plane, which is why it's really relatively easy to go from, say, Earth to Mars. But if Mars was orbiting around like the pole of the sun rather than in the same plane as the Earth, it would be way harder to get to. So solar systems tend to be flat, and planets' rings tend to be flat, and all in the same plane. Galaxies, like spiral galaxies, all tend to be flat. We see a lot of flat systems in the universe, though for the record, Earth is not flat. Earth is a sphere. Technically, it's an oblate spheroid. I have to say it.
We nearly got him, gang.
I have to say it. But the reason that we have all of these flat systems is due to a thing called the conservation of angular momentum, which is essentially, we've talked about momentum on the podcast before, which is a tendency for a thing to keep moving if it's already moving. If you want to stop it doing that, you've got to apply a force, Newton's second law, all that sort of stuff. Angular momentum is essentially an object's tendency to keep spinning around the point it's spinning around. More angular momentum, thing goes faster. But like energy, it's one of these things that laws of physics basically say has to be conserved. Basically means you can't just, if a thing is moving, unless you're going to apply a force to it, its angular momentum cannot change. Which it doesn't intuitively explain why everything goes flat. So,
nope.
Okay, so I'm going to use the example of a solar system because it's the easiest thing to explain first, and then I'll go into everything else. So,
okay, I have a secondary question about solar systems that I would like to interject at some point.
Okay.
Just letting you know.
Okay. The thing you've got to understand about a solar system, about planets and moons and bits of rubble we call asteroids, is that we are all essentially just made up of the leftovers from star formation. When Carl Sagan said we are made of star stuff, he was talking literally. So stars start off as a big gas cloud that something whacks into them or causes some sort of perturbation. It could be like a nearby star goes supernova and sends this big blast wave through that just causes a little ripple to go through your molecular gas cloud, and you get enough of an overdensity to start causing a gravitational collapse. The gas cloud collapses down, heats up, because when you compress a gas, it gets hotter, and it will compress down to a point where you've got this this sort of core of material. We call it protostar because it's what comes before a star becomes a star. But as that collapse happens, because this cloud will have had some amount of angular momentum, a little bit of motion, as it's got smaller, its angular momentum has to stay the same. But angular momentum is bit of maths here, is the product of its speed, its velocity, and its the distance from that point it's rotating around.
Correct.
If you make the distance that this bit of gas is from its rotating center smaller, you've got to go faster. And as it goes faster, you then get centripetal motion, centripetal force. I think it's centripetal.
Yeah.
Yeah. Centripetal force.
That's the one inwards.
Yeah. You've got your centripetal force, which has to be balanced by gravity. And basically, because it's starting to spin around this central point, it gets pulled in, and then as it spins faster, its tendency to fly away as it gets faster is balanced by the inward pull from gravity, and the whole thing gets pulled, I'm going to say, down towards this central plane. Obviously, you've got stuff above and below this where the disk forms. So it gets pulled towards that axis of rotation, kind of like the equator of a sphere.
Okay. So I can conceptually understand from an ellipse, something that's already sort of flat, going flatter.
Yeah.
What dictates going from I suppose it's not a perfect sphere. Is that what dictates what plane the flat bit is?
Essentially, it's kind of a bit chaotic. Initially, you've got broadly a system that's pretty much random motion. So all the gas is going in completely random directions around this sort of overdensity. Ultimately, it just kind of comes down to which random motion has randomly a little bit more motion along that direction. Because these clouds start off like hundreds of light years across, and they will compress down to something that's like 40 to 100, somewhere between about, I mean, depending on the mass of star you're going to get out of it, somewhere between about 10 and 100 times the distance between Earth and the Sun, which is like 8 light minutes, is the distance between Earth and the Sun. They go from very large to very small, maybe not hundreds of light years, but a few hundred, like...
Sorry. Sanity check for the astronomer saying 8 light minutes is very small.
I work on scales of megaparsecs.
I work in microns. Tiny.
When I work in a field that is affected by scales that cover 34 orders of magnitude in scale, this is very small.
I know. I enjoy the again, cultural norms that different academic groups have of like, yeah, of course that's like distance Earth to the Sun, that's nothing. And you're like, that is...
I mean, to be fair, all of this is happening below the resolution limit of my simulations, so... But yeah, essentially what you get is this collapse down to a disk, and the reason it becomes a disk is because as the thing speeds up, it wants to move out, but gravity wants to pull it in, and the way those forces sum is that you end up with a net force that pulls it towards the plane, towards the equator of that overall rotation. It's the same thing we get with Earth coming back to the oblate spheroid thing. If we weren't rotating, we would just be a sphere. We are rotating. The stuff in the middle, it pushes us out, but gravity is pulling in, which for things away from the equator means you get squished a little bit. If you massively sped up the rotation of the Earth would start to become a bit of a pancake.
Okay, so the disk around the equator is bigger. So Earth is a pancake theorist. You heard it here first. You're all right. Everyone else, jury's still out.
I think you'd probably end up ripping the Earth apart through shear forces before it would become sufficiently flat.
So donut Earth is definitely out.
We definitely aren't a donut.
I feel like all the sci-fi... There's got to be a book that has a toroidal Earth.
There is definitely something about, like...
I feel like I've seen it.
Toroidal planet, it's a hypothetical type of telluric exoplanet. Oh, terrestrial exoplanet with a toroidal or donut shape. No firm theoretical understanding is how this could form naturally.
I had an intelligent thought, and I forgot it.
Mood.
Okay, my question from previous, which... Awesome explanation, thank you. The rings of Saturn... Yeah. Saturn is one of the rings.
Well, it's not the only one, but it's the one with the famous rings.
Are they in the same plane as all of the planets moving?
Oh, that's a good question. No, they're not. The reason I know this is because we can go from seeing them to not seeing them to seeing them again as our perspective to Saturn changes.
So they don't cut it through the middle all the time, which is what it would do
if
they were in the same plane.
Exactly. So there was like sensationalist astronomy news articles a few months ago of Saturn's rings are gonna disappear, and it's like, okay, right, it goes through the point where it is directly edge on to us, and then it moves a little bit further, we can see like the face of them again. The reason for that is because I actually have a little bit of it. I prepared notes.
What? Wait, we were supposed to do homework for this?
When you ask me about stuff about space, I do at least have a think. Space is not, as much as we're saying space is flat, because a lot of things in it are. Space is not entirely flat. There is a lot of randomness in space. In the early days of a solar system, that whole environment is very chaotic. If you've ever seen a picture of the far side of the moon, you'll know that it's covered in craters, because there were so many like random bits of rock and ice, asteroids, comets, etc., buzzing around in the early solar system. And you kind of get the same thing with the outer planets. So Saturn has recently, like in the past few months, been confirmed to have has overtaken Jupiter to be the planet with the most moons.
Really?
I mean, moon is being generous. Some of these are just rather large asteroids that have been captured by Saturn. I think we need a better definition of moon.
Yeah, but if they have a name, like, if it's named, it's a moon.
I don't even know if some of these have proper names yet. There's like 300 or something.
We should call one Dave.
I'm sure somebody has. Basically, when you have all of these sort of random things buzzing around, they're not all gonna necessarily become affected by a planet exactly in that plane. So some of them orbit nice in a plane. So around Jupiter, you've got the Galilean moons, the 4 massive ones, Io, Callisto, Ganymede, and Europa, and they all orbit basically in a plane. And a lot of Saturn's moons do. And this is how you end up with the rings, because you had quite a few moons all orbiting in this plane around Saturn that just developed through the interaction of all these moons, kind of defined Saturn's own plane. And as some of them wandered too close to Saturn or too close to another moon, tidal forces, which is basically a variation of the gravitational force over an object, got strong enough that basically it completely tidally disrupted these moons, destroying them with gravity. So you take a moon, you rip it apart, and it disperses into these gorgeous, thin, but very bright rings around Saturn. And that's why there's like multiple rings, like A through G, I think.
Has space finally run out of interesting names to you?
Saturn's not the only planet with rings. Jupiter has a couple, I think. Uranus has some. Neptune maybe as well, but they are a lot fainter, to the point that like you can't see them without a telescope. Some of them you can't even with a telescope, you can't really see them in visible light. There was a James Webb Space Telescope image of Jupiter from, it's probably about a year ago now, that showed Jupiter's rings, but in infrared light where they're more visible.
Which, can we actually just segue onto the discussion about how space is a lie? I know we said we would do why space is flat, but like, images from space are not as pretty, colourfully wise, as we are led to believe.
Depends on the telescope, but yes.
Like, this blew my mind. Can you please explain?
Sure. So there's two aspects to this. If you've got an image from the Hubble Space Telescope, Hubble, primarily, most of its range is in the visible light. It can do a little bit of the near-infrared, which we can't see with our eyes. It can do a little bit of the near-ultraviolet, which we can't see with our eyes either. But most of what it can see is wavelengths from roughly about 400, which is blue, to roughly about 700, which is red. Most of the colours we see in a Hubble Space Telescope image are actually colours we would see with our own eyes.
Yeah.
The space is a lie part of it is, because Hubble is a telescope with a camera, much like any digital camera, you can change how long you expose the sensor for. So our eyes, there's a certain amount of light that our eyes can be sensitive to in a given, like, per second or whatever. Like, we don't have a frame rate, but you know what I mean.
But pretend we do for a second.
There is a limit to how much our eyes can detect. I think in terms of being able to detect there is light versus there is not light, I think we need like a couple hundred photons per second. But then we're only getting, there is light there versus, there is no light there. We can't see colours at that because I think that's the rods, not the cones in our eyes. It's the light sensitive rather than the colour sensitive aspect. Anyway, I might be wrong, it might be the other way around. Hubble, on the other hand, you can expose for hours if you pointed at the same bit of the sky. In that regard, if you looked at some nebula that looks fabulous in a Hubble image, if you went there and looked at it with your own eyes, you might see the same colours, but they would be probably nowhere near as vibrant. The space is a lie other aspect of things is when entirely true for any telescope that does not look in the invisible light. So any colour image you see from the James Webb Space Telescope, those are not the real colours. We will have recorded wavelengths of infrared light with James Webb Space Telescope, and we might have recorded a slightly longer wavelength, a slightly shorter wavelength, and something in the middle. And what astronomers will do is assign one of those wavelengths to be red in the image, one to be green, and one to be blue. You combine all of those things into the image, and that then gives you a colour image we can see and interpret with our eyes, but it's not actually those colours in real life, because the colours in real life are ones we can't see.
So it's sort of like when you're plotting something and you choose a colour map and you have your maximum value and your minimum value, and then it's a range between.
Yeah, it's like how if I can't, like, I'm going to plot temperature in my paper. I can't assign temperature doesn't have a distinct colour.
If I said that red was hot and blue was cold, then people sort of can interpret it that way.
When we make images in astronomy, we assign colours to our data in a way that lets us interpret what's going on.
I mean, I think it's something that once realised makes sense, but genuinely didn't sort of click with me until I saw I think it was a discussion about it on Reddit or something, of like data visualization techniques, and one of the best one being the fact that astronomy has us all conned into thinking that space is beautiful.
I mean, it is.
It is. Don't come for me. It is, but it's not what we see on the front. Like that, you have to interpret it. You have to be able to visualize the data in a way that makes sense for us to understand. Just putting ones and zeros on a screen doesn't do anything.
Yeah.
But yeah, that blew my mind. It also made me think that all images should be done in like MATLAB default color maps, because it'd be funny.
As long as it's not jet. That's the rainbow one, and it's terrible.
Yeah. I mean, have you seen HSV? Sorry to go on. Anyone that knows MATLAB color maps will enjoy our pain. HSV is like the neon rainbow.
Oh, that's worse.
Yeah, and not to put my supervisor on blast or anything. Again, I had a great time doing my PhD. I learned a lot. They were amazing. But I would send images or plots in like Viridis or a nice perceptually uniform color map that was blue themed, so it would go with the water, and I would get images back in HSV. And they're not wrong. You can see more, but it hurt my...
You can see more if you're not colorblind.
This is true. But yeah, so space is a lie, and it's also flat. So it's a flat lie.
Yeah. I mean, just to stay on like the false color images thing, perhaps the best example of this is actually Neptune.
Oh, because everyone thinks it's blue.
Well, it is blue. But everyone thinks it's a dark blue, and Uranus is a light blue. Because we have these images from Voyager 2, the only probe we've ever sent to Uranus and Neptune. And when they were released, we had this pretty featureless light blue sphere, which was Uranus. And then the image that was released of Neptune was a darker blue, where you could see features of the like clouds and various bands and stuff. And this was great. And at the time, they were like, in the press release for this image, it was, this is a false color image. The contrast in this image has been increased. We can see the features better. But that information got lost in the decades since Voyager 2. So everyone had this mentality of Uranus is light blue and Neptune is dark blue. And like in the last year or so, there was a team that took the Voyager 2 data and reprocessed it to be in a true color image. And actually, Neptune and Uranus are pretty much the same color.
I mean, that's kind of disappointing. That's really good in terms of like accurate scientific communication, and it's very important that people understand. But also, like, it's like when they said that Pluto wasn't a planet. You know, you're ruining my childhood with your facts, and I don't appreciate it.
So, shall we go back to space being flat?
Yeah, I had another thought, but I've forgotten it. Why no space vortex?
What do you mean?
Okay, so things spinning.
Yeah.
If I filled a sink with water and then I'm you're gonna shout at me for this analogy, but like this is how my brain is interpreting the words you're saying. If I filled a sink with water and then I like open the plug, it's gonna create a vortex going down to the plug socket, right?
Yep.
Because there's a pull and things spiral downwards.
Yep.
Black holes.
Yep.
Is there a space vortex like pulling towards it?
Vorticity is a thing. Vorticity is still a thing in space.
Thank you for telling me this.
Space fluids is not that different from terrestrial fluids. I think the reason that you don't see like the space plug hole is probably because the systems that we're...
I asked a question you had to think about.
I mean, my intuition on this is that space is three-dimensional.
So are plugs.
They are, but the center of gravity the water is moving towards is about 6,000 kilometers down.
Ooh.
Whereas with a black hole, the black hole itself is the center of gravity.
Wait, how big are your baths if they're 6,000 kilometers deep?
Yeah, the center of gravity is the Earth, though.
Oh yeah, shut up.
So you've got this very localized vortex relative that's center of rotation is maybe 30 centimeters in a relatively large sink. Like, I don't know, like one of those like catering sinks with the plug holes in the middle rather than like towards the back. You know, at most maybe 30 centimeters between the plug hole and the side of the sink, which is tiny compared to the distance between the bottom of the sink and the center of the Earth where the gravity is centered.
This is true.
So a black hole, by comparison, would be more like everything's rotating around the black hole itself. It would be like the black hole basically being like right in the middle of the sink. So everything would just spiral around the black hole itself, which is the central point. So in terms of things in the middle moving faster, yeah, definitely. Because bringing it back to angular momentum, you move closer, you gotta go faster, otherwise yoink, you're in a black hole. And then we'd never hear from you again.
That would be sad, but don't do that, listeners. Don't recommend it at home. Also, don't recommend it at home standing on a spinny chair and holding really heavy books on either side of you and then pulling them in really quickly to see a really fun/dangerous demo of angular momentum. We definitely don't recommend doing that.
Yeah, definitely not. It also works. It also works really terribly if you happen to have a couple 5 kilogram weights lying around.
We just used textbooks when we did it in mechanics. My lecturer actually got on a chair and
I've done this experiment.
It's fun.
It is fun, and
Very
the other.
stupid.
It was actually the guy I was going to mention before we got sidetracked by everything else. Was
Space is a lie.
the standard example for angular momentum conservation, and you move weight from a large distance to small distance. You have to speed up. Is like a figure skater.
Oh, yes.
So figure skaters start spinning with their arms extended, and they bring it together and probably up. Because figure skating, racing, and all that sort of stuff. But you can go from spinning relatively slowly to very, very, very quickly, depending, basically by pulling your arms in very quickly, you move that moment of inertia. Not going to get onto that because I can't remember all the equations for that. Basically, you move all your angular momentum inwards, and that means you have to spin faster.
Yeah. A very similar thing with aerial, so trapeze, silk, or anything that spins, like aerial hoop and lyra and those sorts of things. Of pull in, go fast, but also the reverse. So if you're going too fast and you get dizzy, you just stick an arm out or a leg out and hope for the best. And normally someone will grab you and stop you.
We have the same thing in Scottish country dancing.
How fast do you spin in country dancing?
So we have a thing in Scottish country dancing called either spinning or the other term you'll find for it is birtling.
Which is an excellent word to say in your accent. Can you do that again?
What, birtling?
10 out of 10. Yes.
But yeah, so essentially it's you spin with your partner. I mean, people have seen the sort of Highland dancing sort of thing where you lock arms and arm up in the air, all that sort of stuff. This is a more controlled, and because you hold on a bit more, but you can get a lot faster, and you can get even more. You can get very fast if you spin. If you and your partner pull yourself very close to spin very quickly. But again, if you want to slow down, you just move a little bit further away, and it's easier to stop. And teaching people that is the most important thing in teaching that.
And do you have crash mats all around them when you're doing this, or do you just say if you're going to let go at this point and send them forwards?
No, you don't let people we generally don't let people who haven't done it before do it with other people that haven't done it before, because the people who have done it before know to hold on.
Spoiling all of my fun, but valid.
Yeah, Scottish country dancing has the same thing as Disneyland of don't let go first.
So if you weren't, I think it is. So I'm going to keep asking questions until I believe you. If you were off the plane of the thing rotating, would you get pulled in a spiral?
Depends. Are you moving already?
I might be.
If you're not, gravity is radial. You'll just get pulled directly towards it. If you are, then I mean, if you're anywhere near the black hole, you're going to be bleeding quickly already. You will, because gravity is radial, you'll start sort of orbiting, unless there's, I mean, if you are a point mass, I'm going to assume you are a spherical cat in a vacuum.
No! Fine.
In that scenario, you would
bloody
orbit.
Physicists.
In that scenario, if you are just a point mass orbiting a black hole, then no, you'll not orbit in a spiral. You'll just orbit sort of off axis.
Okay.
It's the interaction of the fluid with itself, as well as the and also the massive change in angular momentum that leads to that sort of pull down to the disk. So if you're just a point mass and you're not being brought from an incredibly large distance, and there's nothing else to sort of dynamically friction your way down towards that disk, no, you'll probably just continue orbiting like a satellite does off the axis.
Yeah.
Because we have polar orbit satellites, and they don't get dragged down to the same plane as the moon.
Center. Yeah, that makes a lot of sense. Because some of the planets are off axis in the solar system, right?
Some of the planets are off a little bit. Most of them are, broadly speaking, in the same plane. Pluto, not a planet, but according to the IAU, don't come for me.
This is a Pluto is a planet podcast.
Yeah,
I'm dying on this hill.
I still think of Pluto as a planet, but
yes.
But
the real Gen Z test, I think. Were you old enough to be taught Pluto is a planet?
I had a poster on my bedroom wall that said Pluto was a planet.
Did it say anything else, or was it just a placard? From
No, it was something like it. I think it was about each of the planets, and it included Pluto. Right, Pluto is off axis. Because I can't remember exactly why, but essentially there's a lot of things you end up with slightly off axis things throughout the solar system. It's under my thing of space is not entirely flat. So
space is flat except
space is flat-ish. So Pluto and a lot of other smaller solar system objects, typically things that have been small enough to be gravitationally perturbed by something else, do sort of orbit off-axis. But there are other things that orbit off-axis, for example, or move off-axis. For example, we have seasons on Earth. We know this. The reason we have seasons is because the Earth is tilted. Like, the Earth's like rotational axis doesn't point straight out of the plane of the solar system. It's rotated by 21 to 23 degrees-ish. And the reason that we're rotated is because we were hit by something. We got hit by a massive rock while we still had a sort of molten surface. We get hit by a massive rock about the size of Mars, I think. We got hit by something pretty big. And it knocked us off axis, and what's left of it is now the moon.
Okay. I don't think the moon is the size of Mars.
No, but bits of it got yeeted further.
I know you're the space boy, but like...
But this is why we have such a large moon. There is an argument to be made that the Earth-Moon system could be like a binary planet, because the moon is very large.
That's quite cool.
If you compare, say, the size of our moon to Earth versus, like, the largest moons of Jupiter and Saturn to how massive they are, we have an abnormally large moon.
I feel like you're going to tell me off because this is like its own podcast episode, presumably. Is that why we can live here?
What? Is what why?
Does having a big moon contribute to being a terrestrial planet, or like somewhere where life could happen?
Not necessarily. I mean, terrestrial planet is just we have are rocky rather than a gas giant. There's no reason necessarily that we would have that having a moon would make us more habitable unless tides matter, but I don't know. I'm not an earth scientist.
I'm going to go do some research and then come back at this in another episode.
It's whether tides matter for life being able to form on a planet that is within the habitable zone of a star. But back to what I was saying, we're off axis because we got hit by something. There are other systems in our universe that are not flat. Like, we think of galaxies as being quite flat because when we think galaxy, we typically think like the sort of grand spirals.
Chocolate.
You might think chocolate. When you think galaxies in space, you think like sort of like really nice spiral galaxies. It's the pictures we always see because they look the nicest. But when you've got like two spiral galaxies that smash into each other, it's what's called a merger.
How very businesslike.
the massive amount of gas getting dumped in this collision basically causes a massive amount of extra star formation, which then kind of blow all of the remaining gas out of the galaxy, and you've got all these chaotic stellar orbits, and you end up with what's called an elliptical galaxy. Very little gas left anymore, and so it doesn't form new stars. So over time, your blue stars die; they go supernova, and you're left with your your stellar population ages, becomes more red, and it doesn't form any new stars, and it's now generally red in colour. Some people describe these galaxies as red and dead.
Aww.
But these elliptical galaxies, they're not flat, they're just a sort of spheroid of stars at that point.
That's quite cool.
And
so you wouldn't get it being like spiky in two directions. So like two planes cutting into each other. Do they?
You can.
What do they orbit around?
There are some very niche systems that can have multiple gas disks, or essentially two gas rings essentially in the galaxy, and they can be misaligned. Or there's a couple of galaxies where there's two rings of gas and they orbit in opposite directions.
Ooh.
It's really funky. You get also like stellar gas misalignments, where you've got like your disk of stars, and then your disk of gas is misaligned because it's like grabbed because it will like float, like this galaxy will have flown by another galaxy and like grabbed a load of gas off it, and just the way those galaxies were rotated at that time, you end up with like your stellar disk and then a disk of gas that's completely misaligned to it, and over time, through dynamical friction, gravitational interactions between everything, they will eventually sort of realign, but there are some like random objects that we found in galaxy surveys that are just really weird. We've also found some like this is just becoming the Weird Galaxies podcast at this point. We have ring galaxies where you've got like a central cluster. Ring galaxies. You
All
have a
right.
central, like your supermassive black hole and a nuclear star cluster, a cluster of stars in the center. Then a big gap, and then a disk of gas. It's a ring of gas and dust around it, and stars.
That's almost starting to sound like my Taurus Earth.
Yeah, but it's not solid though.
But Donut Galaxy went there. Arguably, if you considered the outsidey bit without the insidey bit, Donut Galaxy. Confirmed.
Yeah, there's one of these things called Hoag's object.
Excuse me?
Hoag is the name, Hoag. There's something called Hoag's object, which is one of these ring galaxies. And amazingly, by complete chance, like these things are incredibly rare, but by complete chance, like first image that comes up, if you look on Google Images, Hoag's object. Just above and to the right of the nuclear star cluster, there is another ring galaxy. They're so rare,
Really
but you can see another ring galaxy through this ring galaxy. And we have no idea how this one formed. We have no idea how this happened.
That's very satisfying. Yeah. Because, I mean, presumably it's the odds of the camera lining up to get them in a straight line.
It's not so much the camera, it's the universe lining up in that way. Like, it is our perspective on it.
Well, any 2 points will make a line between them.
Yeah, but it is our perspective on it. But it's not like we've specifically moved a camera to do that. It's just where we happen to be in the universe.
Okay, well that's pretty funky.
Because, like, if again, bringing it back to the space very small versus space very big thing, if that thing is many, many light years away, us moving a few 100 million kilometers is going to do nothing. In terms of appreciably moving how those things appear in the background, it's not going to matter. But orbiting from like one side of the solar system to the other is how we do like astrometry and measure things in space. We should get Sam on the podcast and ask him about Gaia, because that's what Gaia did.
Okay, but if Sam's coming on the podcast, I'm doing a shot every time he says the word sausage. And for our listeners, that will make sense at some point in the future. Yeah. I suppose, yeah, the cone of possible viewing points of those two things lining up is like trying to shoot. I feel like there's going to be an example of like trying to look down the sight of a gun at like a mile away or something.
Yeah, it's like trying to it's trying to like trying to shoot a target, having done a 360 with a blindfold on and getting a bullseye.
And going back, the image that I'm looking at presumably is falsely coloured.
Let me check.
See, now I'm just like, I'm hyper paranoid about every space image I see.
This is a
I'm
Hubble
like,
Space
cool,
Telescope image. Okay, yes, it is a slightly false colour image.
Ha!
The red is slightly longer than we can see, but the blue and the green are broadly okay.
That's fair.
But the blue is about 450 nanometers, which we can see, and the green is 606, which I think isn't quite green, but is close.
Oh, so they scale it to the actual pure RGB in the
yeah, we basically
like in pixels?
Typically, yeah, I mean, these sorts of images are normally made from observations through 3 filters. So filters that let through a specific like wavelength or small range of wavelengths of light, and then that data is then assigned blue, green, and red in when you create the image.
That makes
sense. I should stress, I'm not an observational astronomer. This is just like stuff I remember from having had to look into some of it, and like that's my degree, I guess.
Yeah, and yeah, that whole thing that you're qualified in, but ignoring that bit.
I haven't touched observations in a while, though I'm about to start.
Oh.
Yeah, I realized I didn't
exciting.
mention this like earlier on, but I've like joined an observing collaboration as part of their theory group. So part of my sort of bonus project, not actually part of my thesis, but a bonus project is sort of
because you don't have enough work on. Right
yeah,
now.
pretty much. Is comparing like some of the observed data to. Which tells us about like how the galaxies are moving. Comparing that to simulations of galaxies. Yeah, it's basically looking at it's looking at all the galaxies that rotate weird, essentially. All the ones that aren't nice flat disks.
Okay, I love that. That's a really nice okay, so this podcast episode is basically you just having a refresher course on the stuff that you're about to go and do then.
Kinda.
Well played. Let's pretend that was intentional.
Yeah, we definitely didn't come up with this idea like 6 months ago.
Nope.
8 months ago.
I mean, You think I remember what happened 6 months ago?
I'm more looking at the date in our Notion workspace for this. But yeah, I guess probably to summarize then, space object be flat, but space itself, universe itself is not getting into cosmology, but like our solar system flat, but not necessarily flat compared to some other solar system, because that's all random and relatively localized. In the same way that we can look at other galaxies, they might be edge on, and we see them nice and flat, they might be face on. The universe is a bit random. Flat, because angular momentum has to be conserved. You move in, you have to go faster. Faster means push out. Gravity wants to pull in, we pull it to a nice disk.
The whole solar system is basically stood on a spinny chair.
Yeah, pretty much.
That tracks.
Saturn has pretty rings, they're all flat because angular momentum and destroying moons.
Too many moons.
You've been listening to the Unstable Fluid podcast. If you have enjoyed this, then please do share it with a friend. If you want to follow us over on social media, we are on Instagram at Unstable Fluid Podcast, or if you want to reach out via email, we're at unstablefluidpodcast@gmail.com. If you want to keep talking about the episode, then you can come and join my Discord server where we have a channel dedicated to the podcast. The link is in the YouTube description or in the show notes. And if you want to follow either of us on social media, then our accounts are also in the description or in the show notes. Thank you again very much for listening to this episode, and we'll see you in the next one.